Let's understand the concept of pipelining. The pipelining means multiple instructions, they are executed, okay, during one timing cycle. Means a instruction is being executed, another instruction can also be available on the or on the processing track. So multiple instructions, they overlap during the execution. So for this a pipeline has to be designed, and a pipeline is designed in a way that it has one input and one output, and in between here is the pipeline. So it can be divided into different stages. Let the stages be S1, S2, S3. I am taking here three stages. We can have more than these stages also. So all these stages are interconnected with each other. Means the output of stage S1 will go into S2, and output of stage S2 will go into S3, and then finally the output is there. These two ends are input and this end is the output marked. Okay, so what happens during each stage? Here there are three stages. Each stage completes a part of the instruction. So means an instruction is processed in multiple stages, part by part. Why we use the pipelining? We use the pipelining to increase the throughput. Okay, throughput is a term that means how many instructions can be taken out from a processor after processing in a particular unit of time. So if we will be doing the pipelining, we will be able to process more instructions in a single unit of time. That will increase the throughput, and which is the main objective of doing the pipelining. So during the pipelining, we may have different stages. So the slowest pipeline decide the length of the machine cycle. Generally it is considered to be same. So once the all the pipeline they are working on the same timing, then we can easily find out the time per instruction. So time per instruction can be find out time per instruction in non-pipelined environment divided by number of pipe stages. So if for a non-pipeline instruction we were having 20 and there were only 4 stages, so it means 5 will be the instruction per, you can say, instruction per time per instruction. Let's see the example through a demonstration. Here in the computer system, as we are going to process the instructions, so here we are given with the instruction like A into B plus C, and this instruction is going to execute in a loop, for loop with 7 iterations. So once for the each iteration we have to give the different value A1, A, B2, C1 like this. Fine, similarly A2, B2, C2, etc. So in a computer system where these values are stored, they are generally stored in the registers. Fine. So to show this concept of pipelining, demonstrating it, we will be using registers. And then where to process this thing? Multiply division. For that we need the combinatorial circuit. Okay, which is adder and multiplier as shown in the right side diagram. Okay, so if we want to solve this particular expression for a loop, we need 5 registers as shown and 2 combinatorial circuit, 5 multiplier and adder. The parts of the instruction are executed in different timing cycles as shown in the next diagram. We can see it. So here we had seen there are registers, there are combinatorial circuits, how they are used to implement the pipelining to solve this particular instruction. Let's move to the next slide. Here we can see that if we take different timing cycles 1, 2, 3, etc., and these are the stages, say S1, S2, S3. As we know, A multiple B should go in the segment 1, and whatever is the output of this, let's say it is the X, so that goes into here X plus C. Okay, so what is this? That goes into the final answer R5. So all these stages are shown here using the two registers. and the third stage is for the first one register only. So as per the timing, we can say we feed in the values of A1, B1 into the R1, R2. As during the clock pulse 2, what happens, our A1, B1, they have moved to the next segment where they are being multiplied, and C1 is to preyed upon. Fine. So in the meantime, the new values A2, B2 has entered in the segment 1. Similarly, as we proceed on the timing 3, what will happen, this entire segment is going further in the segment 3, and this is going here to perform a multiple to B2, and new values have entered here. Okay. Similarly, when go for A4, timing 4, A4, B4 enter into the system new values, and our this previous A2, B2 they goes into the R5 or stage 3, and here A3, B3 they goes fine into this way like this. So it keeps on moving. So we say at third clock pulse, our pipeline is consisting of three segments: segment 1, segment 2, segment 3, that is completely full. So once it is full, it has started giving us the output for these, then in the next timing cycle output for next, then next timing cycle output for A3, B3, C3, then in the next timing cycle output for A4, B4, C4, and so on up to end. Okay, so it means it can do the things simultaneously using multiple segments in a simultaneous manner. This is pipelining, how we achieve the pipeline. Okay, now let's move further. So if we talk about the design of a basic pipeline, so we have already seen it needs two ends, one input, one output. It needs multiple stages which are connected with each other. The output of one stage is connected to the input of another. So at the interfaces where output of one, this is stage S1, say this is stage S2, this is the output of one, this thing is known as the interface. So we have to think of this interface. In computers, this interface is provided through the registers, and which is here to store the intermediate results that is generated from the S1 and to be used in the stage 2, okay, or segment 2. So a common control is required to work all the things, to manage all the things. So keeping in mind this basic design principle of the pipeline, we let's work on to design a 4-segment pipeline. Here if we say the 4-segment pipeline, it can be designed or developed using the registers, combinatorial circuits, and one common clock. This is the common thing. This is input, this is output, two inputs. These are the stages. Sorry. So these are the register interfaces marked with green. Okay. So any input of S1 goes to the S2 through R1. R1 stores that output temporarily. Then S2 process on it and it generate an output that is into the R2. Similarly, it gives the output to as an input to the S3. S3 process it and output is given, and that is stored here in R3, and so on we move on. Okay, so we go on in this way. So here is the common clock which is attached to all the registers, and we know all the stages or all the segments S1, S2, S3, S4, they go in order. Okay, so combinatorial circuits are shown in the stages S1, S2, S3, S4. They can be any adder logic, there can be any multiplier, etc. Means to perform the operation. Okay, now let's study the behavior of this staged pipeline, how it is going to solve our problem, means how it is going to help us to achieve maximum throughput. So in the next slide we will be taking an example. Okay, so let's see here. let's see, here we have taken this example, the same pipeline, four-stage pipeline, and we are given with the six tasks. Tasks are identified by the T1, T2, 3, 4, 5, 6. Okay, and this is the timing cycle, and these are the number of stages or segments in our pipeline environment. Okay, so now let's see what happens here. So at time t, at time 1, T1 enters into the stage 1. At time 2, the task T2 that enters into the segment 1, but in the meantime our task 1 enters into the stage 2. At time 3, T3 is the new task, T2 is the task in the segment 2, and T1 is the task that enters into the stage 3. Similarly at timing 4, if we go ahead, T4 is the new task, T3 is the task which enters in the segment 2, T2 is the task which enters in the segment 3, and T1 is the task which enters in the segment 4. And after this it will go out. Similarly, the next process keeps on. So at this point our pipeline is completely full. So once our pipeline is completely full, we say that this is the point from where we started taking the output, or our computer is giving us the output. So this output is able to help us getting the output from the computers. So from this point we are getting the output. So we are otherwise we might have get the first output at T6. So here we are getting the first output as the fourth timing signal, which is a significant improvement in the throughput. So throughput has increased with the earlier output. Now let's move to the next slide. So here in the pipeline stage, let's understand how the time is taken to complete the task. Let we have n tasks, k segments, and a time for each task is Tp in the pipeline environment. Then this is the formula k plus n minus 1 multiple with Tp. That will tell us the time taken in the pipeline environment. Is there any really speed up? Let's see that. For that, we are first checking the non-pipeline and then the pipeline, both the setup. So now if we consider the non-pipelined environment and say Tn is the time taken for one task and there are total n tasks, then the time taken will be n into Tn in non-pipelined environment. So pipelined environment, we have already seen this is the time taken. So is there any speed up? To determine that speed up, we will be using this formula. This formula is that we have to take the non-parallel divided by the parallel environment time. So here the non-parallel time is ntn and the parallel time is k plus n minus 1 t. Okay. So non-parallel and parallel concept. So once we divide on, we get some ratio, and this ratio is known as the speed up ratio. And based upon the value of this, we can determine that we have got some speed up from the pipelining concept. Now let's understand it more with the help of an example. Before going into the example here, let's see whether there is really a speed up. So here a without pipeline, non-pipeline system is shown where three segments or three stages are there, and one task completes it in three timing units. So three such stages, so it will take 9 total divided by 3, so 3 minutes. So if we perform the same with the pipelined environment, we got something like this where the stage 1 comes, and as it moves on we are just using all the stages. Okay, so here what happens in the 5 unit we are getting the output, and total throughput is timing is this, which is really a speed up from the previous one. So now let's utilize this. Suppose we are talking about the example where each task takes 20 nanosecond and total pipelines are 400 is the task. So find out the speed up ratio. To find out the speed up ratio, let's find the time for pipeline system. It is here k plus n minus 1 multiple with the Tp. Tp given is 20 nanosecond. It leads to this value. Now suppose we take the value to be for the non-pipeline system, and non-pipeline system it takes 1 is taking the 20, so for a one pipeline it will take the 4 into 20 means 80 nanosecond in the non-pipelined environment. There are total 100 tasks, so it will take 8000. To find out the speed up ratio, divide the time for non-pipeline divided by time of pipeline. It is 3.88. So if we see, so 3.88 is our speed up ratio. As we go on increasing our n value, so what will happen? So as we go on increasing the n value, means number of tasks, our speed up ratio will tend toward the number of stages or number of pipeline stages, we say, that is k. Now let's see further. So these are the tasks that you people can do.